Okay. Figuring things out here. Now, I said I was going to try to get the homework for chapter 11 up by today, but I didn't quite get it there. I will do that this evening for sure. But we have done everything in chapter 11 that we're going to do. The only other thing that we're going to talk about just a little bit is pressure in the body, as they talk about, as we talk about blood pressure, for example. That's the main thing that I want to talk about is blood pressure. They talk about the two types of blood pressure right here, where they have the systolic and what's the other one?
Systolic and
diastolic, that's right. And essentially what that is that's a gauge pressure measurement, which means it's measured relative to the atmosphere around us. And the systolic is your maximum blood pressure, and your diastolic is your minimum blood pressure. And usually for healthy humans, different ages mean different blood pressures, but usually it's between 60 and 90 for the diastolic, depending on how old you are, and between 100 and 140 for maximum. Lower pressures generally for younger people. If you're around my age, your blood pressure is supposed to be between high 70s and and then you're for the minimum for the diastolic and like the 120 or 115 to 125 or something like that for the systolic. But the pressure is always changing in your blood, so that's why they ask you to sit down and relax when they take your blood pressure. And the blood pressure has a lot to do with a lot of things in your eyes and your heart and your veins and your arteries, everything in your body is affected by blood pressure. If your blood pressure goes too low, you have a tendency to get very faint, very tired, pass out maybe. Gets very, very high, you have a tendency to be a little bit hyperactive, burn energy very quickly. So lots of things going on. But let's talk about how, let's see, do they talk about how they take the blood pressure? Yes, they don't. Anyway, blood pressure is taken by cutting off the blood flow in your body, and they listen to your heart, or they listen to the blood flowing through your veins as they do that. So they cut it off and they listen, and where the blood stops flowing is let's see, I think that one's the systolic. They can hear when it stops flowing, and then as they release it again, then they listen for it to start again. And then that's the other one, whichever one it is. But anyway, just kind of an interesting thing about pressure. And that blood pressure is what is holding your veins open, actually, and holding your arteries open. Your arteries would collapse without that pressure, without that force of the blood in them. And so you have to have it in there. If you don't have it, if your blood doesn't flow, then your veins and arteries will collapse, because your veins and arteries are designed to collapse. They have muscles in them, and they have stretchy tissue in them that are designed to squeeze that blood through your body. so that it helps flow through the body. So it's kind of like balloons in your body.
So when the blood doesn't have enough pressure to resist that squeezing, it just collapses.
That's right. And when it collapses, then it restricts blood flow, and we call that a stroke. Okay? And particularly that's bad in a major artery or a major vein where it can stop blood flow in the entire body or to the brain. But those collapsing blood vessels because of blood pressure problems is really the issue. Now, what causes it? High blood pressure or low blood pressure? Well, it turns out that high blood pressure is an indicator that you might have a stroke. And the reason for that is because your veins or your arteries can get overworked. They can get overstretched. And then when you relax, they can collapse because they've been worked too hard. The other thing that can happen is that if you have lots of buildup of plaque in your veins from eating bacon, then you have a restricted flow in your veins somewhere, and that actually lowers the blood pressure when you have smaller veins or smaller arteries in parts of your body. And so that actually lowers the blood pressure, and then it can collapse there as well. So there's lots of different problems that blood pressure can cause, high and low blood pressure. So that's just a little biological aside.
I think if I remember correctly, in anatomy and physiology class, we talked about how if your veins have valves to keep the blood moving, because there's not a whole lot of pressure on it from the heart at that point, and how if you're like standing for too long, especially if you have problems in your therapist, yeah, and then the valves are for sure.
Yeah, I'm not a physiology expert by any means, so I couldn't really speak to that. But you believe your physiology teacher when he teaches you things like that. Don't believe your physics teacher. The mouse disconnected for a second, and it's disconnected again. What's going on? So now that's fluid statics, and let's just review really quick the stuff that we covered. We talked about density. What density is? It's just the mass of an object divided by its volume. That gives you the density of some thing. Gives you the average density of something. And then there's pressure. Remember, pressure is force that is distributed over an area, right? It's pressure that is applied to an area. So it's force divided by area. The variation of pressure with depth in a fluid. Why does pressure change with depth?
Because the weight of everything of the fluid above.
That's right. The weight of the fluid above it is pressing down on something that is deeper down, right? So you go deeper, you have more fluid pressing down. Does anybody remember what Pascal's principle was?
Mass is always distributed.
The fluid moves.
That's right. It's the distribution of pressure through a system like this, right? When you have a fluid that is non-compressible fluid, in other words, this fluid won't get squished any smaller than it is, and you apply a pressure to one part of it, the entire fluid will feel that pressure, and that pressure will exert itself over here on this piston, for example. It will exert itself everywhere along the walls of this vessel. That pressure goes everywhere in the fluid. That's Pascal's principle. And one of the results of that is the beautiful relationship that we use in hydraulics, right? In hydraulics, we get this equation here where the force on one piston divided by the area on one piston equals the force on the second piston divided by the area on the second piston, which means you can put a very small force on a small piston and apply a very big force on a bigger piston because the pressure is the same, but the areas are different, right? So that's a nice application of that is very practical. And then we talked about gauge pressure, absolute pressure, and pressure measurement. What's the difference between gauge pressure and absolute pressure? Anybody remember? That's right. Gauge pressure is comparing one pressure to another pressure, usually to the atmospheric pressure, right? And then absolute pressure, what are you comparing to? Zero pressure, right? You're comparing to a situation where there's absolutely no pressure, and that is absolute pressure measurement. And then Archimedes' principle, the last thing that we talked about, was this idea of the buoyant force. When you have something that is immersed in a liquid, or in a fluid rather, you have something that's immersed in a fluid. It can be a gas or a liquid, and it doesn't even have to be fully submerged. It can be partly submerged or fully submerged. But however much fluid it displaces, is the weight of that fluid is equal to the force, the floating force or the buoyant force that the object will feel. Whether or not that object floats, it could be an anchor. An anchor feels a buoyant force. As you drop an anchor, it doesn't fall through the water as quickly as it would fall through air, because the buoyant force in water is much more than the buoyant force in air. So it floats a little bit, and it sinks more slowly than it normally would. A submarine, of course, can change its buoyancy. Changes its buoyancy by filling its ballast tanks with water or emptying its ballast tanks of water so it can go down underwater or come back up. And then we have the balloons, right? If you fill a balloon with helium and you displace that amount of air that is the volume of the balloon and replace it with helium, which has a much lower density, then the force, the buoyant force that the balloon will feel, will be greater than the weight of the balloon, because the air that it displaced is greater than the weight of the balloon. Therefore, you get a balloon that floats when you put helium or hydrogen in it. And here they show the force diagram of a buoyant force, an object experiencing a buoyant force. The pressure that it feels on the top is less than the pressure it feels on the bottom because of the differential in pressures with depth. So it feels a greater pressure on the bottom, a greater force on the bottom, and that is what creates that buoyant force in the end. And we thank Archimedes for that. Here's Archimedes' principle. The buoyant force is equal to the weight of the fluid displaced. And there are some variations on that equation that involve the density. For example, if you want the weight of the fluid displaced, you can create that weight or calculate that weight by taking the density times the volume times g. So rho vg would equal the weight of the fluid. So you would have, instead of buoyant force equals weight of fluid, you have buoyant force equals rho, density of fluid, volume, v, volume of fluid, and g, the gravitational constant. And here they show some of these other equations. If you have a fraction of an object submerged, not the entire object, then you can calculate, you can use this equation here. You have the volume submerged divided by the volume of the object equals the volume of the fluid divided by the volume of the object, the volume of the fluid displaced. But then you can also replace volume with mass divided by densities here. And then you can get the fraction of an object submerged is equal to the density of the object, average, divided by the density of the fluid. It doesn't even have to be the displacement. It's just density of object divided by density of fluid will tell you how much of an object will be submerged. And also, we have a very specific form of this, which is called the specific gravity. The average density of an object divided by the density of water is the specific gravity. And if you have a specific gravity that is less than 1, you will float on top. If it's greater than 1, it will sink. If it's equal to 1, it will be in equilibrium, and it will just sit there wherever you put it. It will go underneath the water, but it will sit at whatever depth you sit it at. So that is Archimedes' principle, the last thing we covered. Let's actually go ahead and put together a homework assignment and give you a few pointers on it. You'll find that this chapter, even though we've blown through it very quickly, it shouldn't be terribly challenging as far as homework goes. Let's see what they've got for us here really quick. Chapter 11, questions. Okay. Okay. Nothing in those ones for us. Nothing here either.
Fluid status one down
Where?
there. Just under the physics library option.
Oh yeah. That's the last place we'll check here in just a second.
Last resort.
Well, this is the one that is for the book. I like to look at some other questions that are available just to see if there's anything interesting. So we're looking at fluid statics. All right, let's see. Let's see what they've got for us. Not a whole lot of different problems, but let's take a look here. Which of the following are fluids? I might as well make it. Give ourselves an easy one, right? Equation. So calculating density of a fluid, not terribly difficult. Mass divided by volume. So calculating pressure is just force divided by area, right? And then depth, there's an equation for the depth, the change of pressure as a function of depth. Here's an Archimedes principle problem where they're giving you the apparent weight underwater and the weight of it in the air. Calculate the buoyant force. We're just going to choose all these things here. Here's one that's very similar to your lab that you did. Careful, there might be a trick question in there. I can almost guarantee you there's one in there. I'm going to give you a bunch of. I'm going to give you all these problems. Why not? I'm not going to give you that one. I'm going to give you the boat problem because it's more realistic. Mm-hmm. A little force diagram problem with Archimedes principle. Okay. So it looks like we're good. Add those to our assignment. All right. Let's make sure we got our. Yeah, let's do that first. Make sure that worked. There we go. Okay. So
So are we able to work on it now, or is it,
I'm gonna fix the due date on it and everything.
other than that, it's good?
Should be, yeah.
So I started out, and it's not gonna kick me out for one time?
It shouldn't. We hope not. Save changes. Did I save changes? Come on, save changes already. Okay, so chapter 11. Available always, available until. So today is the 25th. Okay, so there you go. You got a homework assignment up now. And let's move on to our new chapter, which is chapter 12. As soon as we're done doing a few sections of chapter 12, I will open up the discussion for people who have last minute questions. I know a couple of you are still going to take the test. Make sure that you get that done very soon. We don't want to put that off. We definitely don't want it to go into next week. We need to get out of the second test and into our next chapter so we can get done with this book. But today we're doing chapter 12, Fluid Dynamics, the companion to Fluid Statics. There's 7 sections. And we will do probably we'll probably concentrate mostly on sections 1 through 5. I don't always do 6 and 7. Sometimes I do, sometimes I don't. These chapters, these final chapters, except for the last 2, are sometimes required in this course, sometimes not. So, so I don't necessarily feel bad about not covering everything all the time. But now we're going to talk about how fluids behave when they start moving. It's kind of like the kinematics of fluids. Turns out to be a little bit easier than the kinematics of point particles, but the yellow bar is bugging me. There we go. Okay, so flowing fluids now, fluids that are moving, and I like that they use a fireman picture here with the fire hose. I wish they would have shown the stream of water actually coming out. Have any of you ever been hit by water from a fire hose? It's pretty intense. That stuff is coming out fast. And what's the thing that makes the water come out fast from a fire hose?
Pressure.
Well, you could say that, I suppose, because that does play a role. But there's something else that plays a bigger role. How many of you have ever watered your garden in your yard before? And you've run out of hose, but you still have to reach something that's beyond the reach of your hose. What do? That's right, you stick your thumb over the end of the hose. And what does that do to the aperture on the hose? To the hole on the hose? Makes it smaller. Well, that's kind of interesting. And what's the result? It sprays. What happens? It goes farther, and it's smaller, but there's one other thing that it does. Why does it go farther? What's happening to the water coming out of the hose? It's also going faster, isn't it? You actually speed up the water by making the aperture smaller, by making a nozzle is what we call it. And this is the same thing that makes a rocket go, or a jet plane. This is why rockets and jet planes have nozzles on the back of them to make that gas come out faster so that the jet can move forward faster with that conservation of momentum, right? So it's a nozzle, and nozzles are extremely important in this life. We use them in lots of different things. They're used in our cars. They're used in our showers. They're used in farm equipment. They're used in all kinds of things. Nozzles are extremely important. But how is it that it works? Why does it do this? Why does it move things faster? So we're going to have to talk about a few things first before we get into that. And the first thing we're going to talk about is flow rate. This is a definition, kind of like, you can think of it kind of like velocity, but instead of meters over time, instead of distance over time, this is volume over time. So this is telling us how fast a volume of water moves through a particular place, right? So here's an example. We've got this cylinder of space where some volume, this pink volume, is moving forward, has some velocity v, some average velocity v bar here, and the volume is defined by this length d and this area a. So if you multiply the cross-sectional area a times d, you'll get the actual volume of this little pink cylinder. And the flow rate, Q, would be equal to that volume divided by the time that it takes that volume to pass a point P. So here's the point P on the thing, and when this whole volume passes through, however long it took to do that, would be the time. And that's what we call the flow rate. So it's related to volume and also the velocity of an object.
So you're measuring the time it takes to move from one point to another?
Yeah, it takes the whole volume to move from the front of the volume to move. When the front of the volume hits that point, you start your watch. And when the back of the volume hits that point, you stop your watch. And that's what you're it takes that time for that volume to move through that point.
So it'd be kind of like turning on a fire hose and letting like a certain amount of water out, and when the last drops hit the house that's on fire, you stop it?
That's correct. Well, as long as you timed it from when the first drops hit the fire, right?
Okay. Wait. So wouldn't it be from the time you turn the hose on, like when it passes?
It depends on where the point is you're measuring from. So if the fire is your point that you're measuring your time at, then you measure from when the first drops hit it to when the last drops hit it.
Okay,
and
I
that
thought it
would
was
be
2 points. Like you
no,
mentioned.
just 1 point.
Okay.
So as the volume goes through 1 point or hits 1 point. So that is what we call the flow rate. Q equals volume over time. But you can also rearrange the equation according to the geometry here to make it equal to the area times the length, the cross-sectional area times the length, divided by time. Or you can have the cross-sectional area times the velocity of the fluid. So any one of those will give you the flow rate. And you can also mix up this equation to solve for different things. If you need to solve for the cross-sectional area and you know the volume and the time, you can do that. Well, as long as you know the distance as well. Or if you want to know the distance and you have the time and the velocity, you can calculate that. So there's lots of different ways to mix this up so that you can solve for what you want to solve for. So here's an example of using this flow rate, calculating this flow rate. We're going to calculate how many cubic meters of blood the heart pumps in a 75-year lifetime, assuming the average flow rate is 5 liters per minute. So liters is a measure of volume, minute is a measure of time, and so we want to go ahead and calculate this in SI units, which are cubic meters. So what is a liter? It turns out that a liter is a box that is 10 centimeters by 10 centimeters by 10 centimeters. And in a meter cubed, there are 10 of those by 10 of those by 10 of those. So 10 times 10 times 10. There's 1,000 liters in a cubic meter. Okay? And so the conversion would be 1 meter cubed for every 10,000 liters. That's that conversion right there. And of course, we have minutes and years that we're going to be converting. So it's 5.26 times 10 to the 5th minutes per year. And that gets rid of our minutes and years there. Then we multiply the flow rate times the time to get the volume, rearranging the equation for flow rate. And we get 2 times 10 to the 5th cubic meters of blood. That's a lot of blood. in case you're wondering, all right? It's about 200,000 tons of blood. About 200 times the volume of water in a 6-lane, 50-meter lap pool. So it's probably about 100 times as much water as in an Olympic pool. It's a lot of blood. Let's see here. Now, we're going to introduce you to a new rule, a new law here of fluid dynamics.
Conservation of it?
Conservation is one way to say it. We usually call it continuity. Okay? So here is, if we're going to assume right now that the fluids that we're dealing with are not compressible. In other words, they're liquids. And liquids cannot be compressed very easily. It's very difficult to squeeze them into a smaller volume. So we call them incompressible. If you have a volume in a pipe like this that has a very big radius, and you have this volume that is made up by this little dark purple cylinder here, and it is traveling at some velocity v1 through this big pipe here, and then all of a sudden it encounters a much smaller pipe, what's going to happen? Remember, this is not compressible. This fluid cannot be squished. It can be rearranged into different shapes, but it's going to keep up the same volume. What's that? Okay, first of all, it's going to change. It's going to be a longer cylinder, but it'll take up the same amount of volume. Right?
It has to move faster.
What's that, Cassidy?
It has to move faster.
Why does it have to move faster?
Because
Yeah,
it's not going
Is there the same amount of pressure on that back end of the cylinder as there was before?
But
There is a pressure thing going on here, but we're not. But we can't talk about it yet because we're not sure what's going on.
because the liquid isn't going to change its form or how much it is.
Okay, so it's not going to change its volume, right? So you have the same volume. In here, you have a great big cross-sectional area, so it can move slowly along. But in this pipe, it's all crowded together into a, well, it's not all crowded together, but it's a much smaller cross-sectional area, and it has to be longer. And so all of a sudden,
it has to be kind of hitting.
You have to
the
get-
same volume, the same.
yes, the same amount of volume has to pass in the same amount of time. And since the same volume over here has a much longer length, this piece has to be going faster than this piece.
Same principles when you put your thumb over the hose.
And it's the same principle as putting your thumb over the hose. That's what makes the water go faster because it cannot be compressed, that fluid has to move faster. I like to think of it as a freeway. You have a freeway with 1 million cars on it. We're in California, okay? And it's 10 lanes. You know you're in California. Okay, and that's not a joke. There are 10-lane freeways in California. I think there's even 14-lane freeways in California. One side. Okay, that's just one way.
That would be crazy.
The other way is just as big. The one outside my town is a pretty small one. I think it's 6 or 8 now. There used to only be 3 or 4 when I was a kid, but now it's twice as big. But anyway, the point is, you got this freeway and you got 1 million cars on it that pass every hour. So you're sitting there by the freeway, and I could see the freeway from my house. I couldn't really hear it because it was a few miles away, but I lived up on a hill so I could see it. And I'm sitting at my house at the pool, enjoying a lemonade and watching the craziness go by. And I count 1 million cars in an hour. But that was when I was a kid, when it was 3 lanes. And so they had to move pretty quick. But now that there's more lanes, more cars can go by every second or every whatever. And it would take, the cars don't have to go by as quickly if it's 8 lanes wide for it to get 1 million, right, going by. So you think of this as a freeway where when it gets skinny, the cars can go as fast as they want to keep the same number of cars going through, right? Of course, on freeways, we don't make laws like that. When the freeway gets skinny, double your speed or whatever. But if we did make a law like that, and if people could drive safely and efficiently that way, then the freeways wouldn't get bottlenecked. If you could go twice as fast on a freeway that's half as wide, you would never have bottlenecks.
So theoretically, if you were going 100 on it's a 2-lane highway where the other lane is head-to-head, but then you move to
The
the
4-lane,
freeway, you could go like 45 miles an
Yeah, I mean, theoretically, that would make traffic better. Except when you crash at 100 miles an hour, there's zero chance of survival.
Unless you're in like an Indy car or something that's specially designed. to
Even
survive.
Indy cars, not many Indy drivers survive crashes at 100 miles an hour. Very few of them do.
There was one that I saw where the driver said it was probably this far from the
Yeah, it's
pavement. A lot closer than that, probably, actually.
it's pretty bad when they crash. But anyway, so this is called the law of continuity, which means the same amount of fluid has to pass, the volume of fluid still has to pass, the same volume of fluid has to pass a point in any pipe that is connected to this flow of fluid in the same amount of time. And because that is the case with the different areas, cross-sectional areas, you get an equation that looks like this, where area 1 times velocity 1 average has to equal area 2 times velocity 2 average. In other words, the flow rates have to be the same. The flow has to be the same in an incompressible fluid in an enclosed fluid system. This brings all kinds of interesting things to bear. Of course, how many of you have been river rafting? Never been river rafting? You ever seen a river, like a real river that has narrows in it? If you ever go river rafting, you'll know that this is true, or if you go canoeing on a river, or anything else on a river, you go to a real river that has wide areas and skinny areas, you'll know that the flow is different from wide to skinny. In the wide areas, it slows down, and the skinny areas, it speeds up. The rapids are the skinny areas. That's where people like to do their rafting and their kayaking and everything else. So it's just like that. So anyway, let's calculate fluid speed when a tube narrows down. We start off with we have a nozzle that has a 0.250 centimeter radius, and it's attached to a garden nose with a radius of 0.9 centimeters. And the flow rate through the hose in the nozzle is 0.5 liters per second. We're going to calculate the speed of the water in the hose and then in the nozzle, right? So Q equals the cross-sectional area times the velocity of the fluid. That's one of the equations that we have for flow rate. And if we rearrange that to solve for the velocity, for velocity 1, we get flow rate over area 1. The area is a circle, so it's pi times r1 squared. And we go ahead and put on our numbers here. We get 1.96 meters per second. Make sure that you do conversions. They convert the meters or the liters to cubic meters, and they converted the centimeters to meters also. Then once you get that done, you got 1.96 meters per second squared for the velocity in the hose. 1.9, so to 2 meters per second. I can believe that when I'm holding a hose, the water coming out goes 2 meters in a second, approximately 6 or 7 feet in a second. That makes sense. And then we could do this again for the other one, for the nozzle, but we also could just use the continuity equation. Continuity equation says that area 1 times velocity 1 equals area 2 times velocity 2. We have area 1 and velocity 1, and we have area 2. We plug in those numbers, and we get velocity 2 ending up equaling 25.5 meters per second. So you put a nozzle on that constricts something by 1/4, and you get almost 10 times the speed. A little more than 10 times the speed. Coming out. So especially in natural systems, but also in man-made systems, you may have what we call branching or capillaries, the capillary effect, where you go from one hose to many hoses, right? And there is still, or you maybe go from many hoses to many more hoses, or something like that. And this is also covered by the continuity equation, but in that version of the continuity equation, you have an n for each side, which tells you the number of hoses in that particular section. So if you go from one artery to 500 capillaries or something like this, then the one artery, n equals 1, would be here with the cross-sectional area of that artery and the velocity of the blood of that artery. And then your 500 capillaries would be n2, And then area 2 would be the average area of those capillaries, and velocity 2 would be the velocity of blood in those capillaries. What's going to happen to the blood in your capillaries as you go from an artery to a capillary?
Pressure decreases.
We don't know anything about pressure from this. What do we know from this? What's that? What happens as you go from big to small? Yeah, it increases the velocity. But if you have, that's if you have 1 to 1. So what if you have 1 to 500? Well, it depends on the size of the capillaries, and it depends on the number of the capillaries. So it could go faster or slower either way. It could actually stay the same. So that's kind of interesting. Because of the n in there, it actually could be even. It could be slower, could be faster, could be the same. So you got to be careful because that n changes everything. If, for example, if your area of your capillaries is 500 times smaller than your artery, and you have 500 capillaries in one artery, then it would be the same, right? So you have lots of different things. So let's do an example like this. We have the aorta, which is the principal blood vessel, and circulates things through the body. Calculate the average speed of the blood in the aorta if the flow rate is 5 liters per minute, and the aorta has a radius of 10 millimeters. Blood also flows through smaller vessels called capillaries. The rate of the blood flow is 5 liters per minute in the aorta. The capillary is about 0.33 millimeters. Average diameter of the speed of the blood is 0.33 millimeters per second. Average diameter is 8 microns. Calculate the number of capillaries in the blood circulatory system. So in this case, our blood flow goes from 5 liters per minute and then the speed in the capillaries, they don't tell us the blood flow there, is 0.33 millimeters per second with a capillary size of 8.0 microns. So we could calculate it there. I think it's going to speed up just from looking at it, but anyway. Let's go ahead and calculate the flow rate. Let's see. They want to know, first of all, the average speed of the blood in the aorta. So they do that. They calculate that from the flow rate equals A times average speed. Rearrange that so it's flow rate over area. Flow rate over the area of the aorta. Pi r squared down there on the bottom. 0.27 meters per second. And what was the speed? 0.33 millimeters per second, right? So it actually slows down pretty dramatically in the capillaries because they're so small. And then for part B, they want us to calculate how many capillaries are in the body using those ends, right? We now have the speed in the aorta, the speed in the capillaries, the area of the aorta, the area of the capillaries, and we want to calculate, we know the number of the aorta is just 1, but they want us to calculate the number for the capillaries, which is N2, and we rearrange that equation, put in our areas, we put in our speeds, and we put in our ends, we put on our N1 for the one aorta. We get 5 times 10 to the 9 capillaries, 5 billion capillaries. That's a lot. But they're everywhere in your body. Capillaries with blood in them are what makes muscles kind of pinkish red, right? It's what makes red meat red. All right, so that was a lot to cover in the first section. That was probably our longest first section of the whole book. Now we move on to one of the consequences of this, of these things that we've learned about, the flow rate and the continuity principle. When we combine it with some other things that we know about, we can learn about a principle called Bernoulli's principle. So it turns out that conservation of energy is also something that is involved with liquids. Remember when we were doing conservation of energy, we had the net work is equal to change in kinetic energy. Excuse me. But in fluids, there's another thing going on. There's another carrier of the energy. We have, just like in other things, we have the velocity of the fluid. We have kinetic energy. Fluids have a kinetic energy. And fluids can even have a potential energy if they're at a higher height and then they go to a lower height. That's a change in potential energy, and it can speed up the fluid, and conservation of energy can occur. But the fluid also has pressure, which is another way of transporting energy. It's another type of energy storage device, you could think of it as. So higher pressure fluids have more energy. It's kind of like a potential energy that they have stored in them. And lower pressure fluids have less of that same stored energy.
So the way that kinetic energy is conserved is almost through pressure?
Well, no, it's just another way that fluids can store energy. It's another form of potential energy for fluids. So it's
Potential or kinetic?
it's a potential energy. Pressure is a potential energy, not a kinetic energy. Because kinetic is movement energy, so it's always related to the velocity. Whereas pressure is related to not so much the movement. Well, not the macrocosmic movement. It's related to the microcosmic movement. But anyway, the point is that it is a form of energy, and we should be able to include it in our conservation of energy equations. So here is what Bernoulli put together. He said, well, we have our potential energy. Instead of using mass in his equation, he's going to use density. He's going to use mass per volume because the fluid is always moving. And so it's better, instead of to just define it as a single mass, to say, well, we're just going to define a particular volume within this fluid. We're going to talk about just this volume as it moves around through the fluid. So we have potential energy, which is density times G times H instead of mass G, instead of MGH, we use density G times H. So that's kind of like our potential energy. That's not exactly equal to potential energy because it's not mass times G times H. So it's like potential energy per volume. Then this would be kinetic energy per volume, 1/2 rho times v squared, and this would be the kinetic energy kind of thing for this particular volume of fluid we're following around, and then the pressure of this fluid as we follow it around. So we're following this fluid around through the system, this particular volume of fluid that we've outlined with some dye or something, and it's got a pressure, it's got a movement energy, a kinetic energy, it's got a potential energy, and we're going to say that that has to remain constant as it goes around through the system, as long as there's nothing that's going to add energy to it or take energy away from it. Okay? So for example, if you're going through the system and then all of a sudden you encounter a pump which speeds you up or increases your pressure or raises you from one height to a higher height, then that would mean that this wouldn't stay constant. However, you can have this conservation of energy as long as nothing is adding energy or taking energy away. And if you measure this at two different points, then you can say that pressure at the first point is equal to 1/2 rho times the velocity of it at that first point plus the rho times g times the height of it at that first point equals the pressure at 2 and the 1/2 rho v squared at 2 and the rho gh at 2. So you can compare two different points. Whenever you can build equations in physics, you can use them to solve things, right? And so this equation is something you can build in general and then use it to solve for things that are going on in fluids. And that's the beauty of it. Now again, this is for an incompressible fluid. There's also going to be no friction. That's what would take energy out of the system, friction. So it's going to be a frictionless fluid. And that is great. Now, Now, what are some of the implications of this? Here is one of the implications. What if your fluid always stays at the same height? So H doesn't change. That means that the rho GH thing on each side would be the same, and you could subtract it from both sides of the equation. It would disappear, and this would be your equation. Pressure 1 equals 1/2 rho V1 squared equals pressure 2 plus 1/2 rho V2 squared. Now let's play with this equation a little bit. So this is what it looks like. Here's a pipe. We have a pipe, and what did we decide happens when you go from big to small in a pipe, or small to big? Which one of these here's our volume of water, or volume of fluid here, right? And in that small pipe, it takes up that big thing, that long thing, and in our big pipe, it takes up this little skinny space here, right? Which one did we decide was going faster?
One on the left, the small one.
The small one is going faster, so it has a velocity that's kind of big, velocity 1. We'll call this one fluid 1 over here. And then fluid 2 has a smaller velocity, velocity 2, right? And our equation looks like this. It looks like pressure 1 plus rho, so it's rho times, it's 1/2 times rho times V1 squared equals pressure 2 plus 1/2 rho, because it's the same density, fluid's the same fluid each time, V2 squared, right? But we just said that V1 is a big V. It's huge. And not only is it big, but we square the thing. So this thing gets really big on the left side of the equation, right? And then this one is really tiny over here. So this is big. And this is tiny. What's going to happen to our pressures in order for this thing to be equal?
Pressure on the left is tiny, pressure on the B.
This one is tiny, and this one is big.
It's kind of the same thing as like conservation of momentum, except with a couple other things added in almost.
Right. So when your water goes from a big pipe into a tiny pipe, what happens to the pressure?
Increases.
Look at the equation.
Yeah.
You said it increases. What did you say, Pagan? You said it decreases? Why does it decrease? Because the speed increases. It's counterintuitive. You would think that to get in that tiny spot, your pressure would have to go up. But what did we say about this fluid? What can't we do to this fluid?
Compress it.
We can't compress it.
So pressure is constant.
No, pressure is not constant. The pressure increases. The pressure increases when you go to the big pipe, but not for the reasons you think. And it decreases when you go to the little pipe, but not for the reasons you think. But what does change is the speed. That we already figured out. And because we know that the speed increases there, we also know that the pressure is going to have to decrease there. So when you go from a big pipe to a small pipe, pressure decreases. You go from a small pipe to a big pipe, pressure increases. Okay? Pressure and speed are not the same thing. Okay? The speed of the fluid going up does not mean that the pressure has gone up. Okay, so pressure means something differently than we think it does. Let me give you an example of why it is different than we think it is. My wife weighs less than half what I weigh. Okay? And yet it would feel better to be stepped on by my church shoes than her church shoes. Why?
Because the heel.
Because sometimes my wife wears heels to church, which have that sharp little point. And what happens to the pressure when you have even half the weight on 1/10 of the area? You get force over teeny area. And if it's over 1/10, it's 10 times the pressure, right?
Which is like why
Whereas my shoes are always big, flat, flopping things, and the pressure just gets spread. I mean, the force gets spread out over this big old area. No big deal. What's that?
snowshoes.
That's right. This is the reason that snowshoes are much bigger than your feet or your boots. It gives you a bigger area so that's less pressure on the snow, so that you don't sink. Skis are the same way. Skis can stay on top of snow because they have a large area, right? So, in fact, well, anyway, we won't go into that. But, so this is Bernoulli's principle. This is Bernoulli's principle when you're not changing height. And this is the reason for This is the reason that rocket nozzles work, and it's the reason that hose nozzles work, and it's the reason that all these cool things work. Another way that I think of this is to think of this microcosmically. We haven't discussed this yet, but we will in this chapter, and that is the idea that fluids are like a big group of tiny little boxers. They're particles that are moving around and hitting things. And I think of them as boxers that are always hitting at this particular rate. They're like punching 1 time per second at whatever they're next to. And when they're next to this little small area here, they're punching 1 time per second. Every little particle in the fluid is punching the wall 1 time per second, but it's moving faster. So they don't get to punch the wall as many times as they're going through this skinny area. But when they get out in this big fat pipe here, they're moving really slowly, so they get to punch the same part of the wall a lot of times before they move on to the next part of the wall, right? Because they're moving very slowly along the wall. And that's kind of how it is. That's actually a much more accurate description of what pressure is. Pressure is the pushing of particles against other things, like against some kind of area.
That's probably going to help me remember the tiny boxes.
The tiny little boxers, right. And we will think about that some more. So when they're moving quickly, they don't have a chance to punch as much. When they're moving slowly, since they punch at the same rate all the time, they can punch more. Okay, so that is Bernoulli's law when there's no change in height. But the same thing you can do the same idea when you change height as well. You could change the height of this pipe and go from a small pipe to a big pipe. But then you would have a change in potential gravitational energy from one to the other with this height h. That means you would add to each side of this a rho g h 1 plus rho g h 2, and then you have one more thing that can change on each side. You have your volume of fluid down here, changes to a different volume up here. Well, same volume, but a different shape up here. And you're good. So that can affect the velocity going up the hill or going down the hill. Of course, if you're going down the hill, you're going to speed up even more going from the bigger pipe to the smaller pipe. And if you're going up the hill, you're going to slow down even more going from the smaller pipe to the bigger pipe, right? So things can change quite a bit there. Bernoulli's principle. Oh, well, let's do this problem real quick. So, using Bernoulli's principle, we're going to measure something. We're going to calculate something. We found that the speed of water in a hose increases from 1.96 to 25.5 in the last example, in the hose and the nozzle. But we're going to calculate the pressure in the hose, given that the absolute pressure at the nozzle is 1.01 times 10 to the 5th newton per meter squared. Why? Why does the water that's at the nozzle, that's coming out the nozzle, have to be at atmospheric pressure? Because it's in the atmosphere, and the atmosphere is the only thing pressing on it, right? So once you're out in the atmosphere, once that water's out in the atmosphere, it's at atmospheric pressure. So we know that atmospheric pressure is the pressure of the water at the end of the nozzle, and we're doing level flow, so we can use Bernoulli's principle without the height thing, without the change in height. And we plug it in, we solve for the pressure 1, which we want to know, and we get pressure 2 plus the kinetic energy part minus the kinetic energy from the second part. Simplify it a little bit and plug in our numbers. Make sure you make all your conversions that you need to make, and you get 4.24 times 10 to the 5th newtons per meter inside. So more than 4 times the pressure inside the hose than outside the hose. Okay? Now, here are some applications of Bernoulli's principle. We have, this is called entrainment.
Oh, that's what I've heard the name Bernoulli.
Oh yeah, you've heard Bernoulli a lot before. So entrainment is the use of pressure and movement of fluids to actually create an upward flow or an outward flow of something. So in the case of flues, which is this one and this one here, you get you have, in this case, you're burning natural gas here, and you draw in the air here. Well, how do you draw in the air? Well, the natural gas is burning and it moves upward and it creates what kind of pressure in here compared to out here? You get fast moving gases inside here. Fast moving gases, high or low?
Low pressure.
Fast moving gases are low pressure. If you have low pressure and high pressure, the fluids tend to flow from areas of high pressure to low pressure, so it draws in the air here on its own. You don't have to pump it in at all. And this is how, this is, for example, how, they're actually calling this a Bunsen burner, but this is also how you bring in air into older cars with the, what do they call that device? Carburetor. Newer cars actually inject the air and the fuel in, but with their fuel injection systems. But this is also similar to how a carburetor works, although this might be more of a carburetor. How a carburetor works. But what's
I
that?
think B is kind of how it works.
B is
Because it's the air kind of moving across, and then because it's moving fast.
well, probably yeah. I guess that's true as well. So this is what is called a atomizer, and they use them for perfume. And you just have a tube that goes down into the liquid here, and then you squeeze fast moving air across the top, and it actually lowers the pressure above the liquid to the point that the liquid actually releases individual atoms of air. So it actually turns it into a gas. And then you don't use very much perfume, because perfume has a tendency to be very strong, and you really do want just atoms of perfume, not lots of liquid. If you pour perfume onto it, it's really strong. Some people still tend to do that, but it's called an atomizer, and I guess that it's actually kind of a combination between these two, I think, as well. But I'm not exactly sure, but it's the same idea. In this case, you have water moving down very quickly and drawing air in C, which is an aspirator. So these are used for creating vacuum pumps. And then this here is what you have at your water heater or your heater in your house. You have the hot air that's coming from inside the water heater or the heater itself, and it draws in air from the basement or in the house to drive it up the chimney. And the more air you can draw, I mean, you do the same thing in a fireplace, except you draw the air in from the bottom below the fire. So a good fireplace actually has a vent underneath it. My fireplace has one of these. It has a vent underneath it, and it has vents in the bottom or the sides of the fireplace that draw oxygen into your fire, usually from outside the house so that you don't suffocate inside the house. And it draws that air in so that you can feed oxygen to the fire. Let's see here, and that's called entrainment. So wings follow this, they use Bernoulli's principle for flying and for sailing. This is how you sail a boat, this is how you fly a plane, right? You shape the wing in such a way that the air that goes over the top is going a longer distance than the air under the bottom. And they still have to catch up to each other, even though they take different paths. The continuity equation is still valid. So the one that goes over the top and goes a longer distance has to go faster to get around. It goes faster, which means lower pressure, higher pressure underneath creates the lift. Now that's not all of the lift of an airplane, it's also the angle of the wing. The angle of the wing creates lift by creating a conservation of momentum situation, where the momentum of the air is changed by being pushed down by either the wing angle or the flaps angle, and then the conservation of momentum, of course, means the plane has to go up. So there's both of those things. And it turns out that for the longest time, many engineers and scientists believed that Bernoulli's law played more of a role. And it does when you're flying level flight. But when you're taking off, or you're landing, or you're doing any other kind of maneuver, turning, banking, climbing, whatever else, it's actually the other one that probably plays the bigger role, they're discovering. Because you can actually fly a plane upside down, you just have to adjust your flaps. So you can fly a plane with the wings backwards.
Wasn't there a movie about that or something? Planes out of Washington, I think?
I couldn't tell you. There have been a lot of movies about airplanes. but for sure, Bernoulli's law is involved here. With sails, the same idea. With sails, you have the angle of the sail speeds up the air in one direction, slows it down another, creates lower and higher pressures. So on the back side here, it's actually slowing down. In this front side, it's speeding up, and you have the low pressure and the high pressure here. In fact, many racing sailboats and high they actually make many sailboats now that actually have an airfoil or a wing instead of a sail. With the proper materials, you can make a wing boat that is very efficient. And here is a device that is used for measuring fluid velocities. And this actually is used, this is similar to the tube that is the device that's used to measure speed in an airplane. In an airplane, they usually put one of these tubes pointing down and one of them pointing forward. So that you have the pressure perpendicular, the pressure on the bottom of the wing, which would be the pressure that you're comparing to, and then the one pointing straight forward. And so if you know what the pressure of the air is outside, and you can measure the pressure of the air that's coming in this way, then you can actually measure your speed. You can measure the speed of the airplane on it. And that's how the speed indicators on airplanes are used. The difference in pressure. And Bernoulli's law. So. And the equations for that manometer are here. The height is proportional to proportional to the velocity here of the fluid. So you get this change in height here that is due to that pressure difference. So lots of things that are affected by our friend Bernoulli. And then Torricelli's equation. So here's Bernoulli's equation. It's got the rho V, the rho GH, and everything else. And then if the pressure is the same at both ends, you can get rid of the P1 and the P2 here, and you're just left with this equation, which looks a lot like our old conservation energy equation, but each one of these terms has a rho in it. So you can cancel out all the rho's, and you can get this equation here, which essentially is going to tell you the difference in speed of a fluid if the only thing it does is change height and it doesn't change pressure. So this is the equation that you use, for example, if you're going to calculate the speed of the water at the top of a dam, or the speed of the water that is dropping in a reservoir as it's dropping and the dam is letting the water out, compared to the speed of the water coming out at the bottom of the dam. The speed of the water coming out the bottom of the dam turns out to be a lot bigger than the speed of the lake going down, but this is called Torricelli's equation, or Torricelli's theorem. So here is the picture. You have the dam right here, and you have the dam water up here, and it's going down slowly, 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 and then it's coming out here super fast. And if the reservoir is big enough, you can actually consider this velocity to be zero. It's so small. And then the equation actually becomes even simpler. If velocity 1 is 0, then velocity 2 is just equal to 2 times GH. And it's simple as that. You can also use this for, well, you can't use it for this fire hose. They're going to do a example of this with, example of Bernoulli's law with the fire hose, where you have a pressure at the bottom and the pressure of the top being the pressure of atmosphere. So they give you the first pressure, 1.6 times 10 to the 6 Newton per meter squared, and then the second pressure would be the pressure of atmosphere, 1.01 times 10 to the 5 newtons per meter squared. Newtons per meter squared are the pascals we talked about earlier. And then they give you they give you the diameter of the hose and the diameter of the nozzle, so that you can use the flow rate equation to calculate the speed of it coming out the nozzle. And then you can put that in for your speed 2 here, and your speed 1 is the diameter of the hose. And then it changes height, And so you put in your original height and your final height. The original height's probably 0, and your final height's the height of the ladder or whatever it is. And then you go ahead and calculate whatever they want you to calculate at the top, which I don't know what it is.
So you go through all that stuff just to get the pressure to 0?
Let's see here. Yeah. So what they want to know is they want to know the pressure of the water coming out the top, and it turns out to be 0 gauge pressure, right? So it's 0. There's 0 change from atmosphere. And is that true when it comes out of the nozzle? We already talked about that, right? What kind of pressures are acting on the water once it leaves the nozzle?
Just atmosphere.
Just atmosphere. So there's no difference for atmosphere. So its gauge pressure is 0, right?
Its absolute pressure would be different.
Its absolute pressure would be 1.01 times 10 to the 5th. But here they're measuring gauge pressures. So they use a gauge pressure. It's a gauge pressure of 1.62, so that's above atmosphere. So
what it's saying is basically when it goes up the ladder, it's basically losing a lot of its.
there is a
It doesn't
change.
have much pressure, but it'll have a lot of velocity.
It required pressure to get up that hill. The pressure is the energy, is the potential energy that was able to push it up that hill. If you didn't have
when it
that
goes up the
pressure-
hill, it exchanges pressure for velocity.
It exchanges pressure for height.
Okay. And it keeps the same. Doesn't keep the same velocity, but it still
It
has
keeps the
some.
same velocity in the hose, but once it comes out the nozzle, it changes velocity.
Okay. So changes the pressure for height, and then still has enough velocity to be able to
That's
shot on
And that's the same reason that when the water is at the top of the dam and at the bottom of the dam, it's the same reason for the change in speed there. Because at the bottom of the dam, it's going much faster out here than it is at the top of the dam here, right? And the thing that provides the energy for that change in speed is the pressure, again. Right? But that pressure is caused by the height of the water this time. So, anyway, so what if we wanted to make some power with this stuff? If we want power from flowing fluid, like in a hydroelectric dam. Well, remember, power is energy per time, and all the stuff in Bernoulli's equation is energy per volume. So we need to multiply everything in Bernoulli's equation times volume, and then divide by time that it takes to get this out. So you have the hose. Here they're going to calculate power in a moving fluid. We have a hose that's fed by this pump. It's got this diameter. It's coming from this hydrant with the pressure, just like we did before. But it turns out that we can calculate that power by using the flow rate, which has the volume in it, but it also has the time. So the volume divided by time. We need to multiply by volume, divide by time. That is flow rate. So if we take the pressure and multiply it by the flow rate, it'll tell us how much power we can get from a certain pressure of the fluid. So it's pressure times flow rate. Pretty simple. And that comes out in watts. Comes out 3.68 times 10 to the 4 watts in this case, which is 36.8 kilowatts. So that's an easy equation. The power that you can extract from a fluid, or the power that a fluid can impart, is the pressure of the fluid times the flow rate of the fluid.
So that's why you would put your turbines for hydroelectric dam at the bottom of the dam.
That's exactly right.
Increased. Would you say it would have an increased flow rate, or it could just be?
The flow rate will be the same. The pressure will be increased.
Pressure.
The pressure, due to the height difference,
Yep.
has increased.
Which will provide more power.
That's correct. So in any dam, in any kind of dam, the generators are always at the bottom of the dam. The turbines. That is correct. What time is it here today?
446.
All right. I'm going to save laminar flow. Got all these great French names. Poisson law. I'm going to save viscosity, turbulence, stuff like. I'm going to save this last couple of sections for tomorrow when we will open up a chapter 12 homework. And right now, I'm going to entertain any questions that anybody has, mopping up the last few chapters before the exam. So let's go ahead. I'm going to take just a little short break to get a drink because I'm thirsty from talking, and then I'll be back to answer some questions. Okay. So I know that some people have had some questions for me concerning the last few chapters here. I've had several emails. So now is the time to cover those questions. What do we got?
So we can go back to some of the other ones and get some questions answered here.
Absolutely. Any question will do.
I think I had some in the show.
Somebody asked me the question about a question on the exam being crossed off on the homework, but I thought it was one that I crossed off on one chapter and then I put on the next chapter. But I'll go and check that to make sure. I can't remember which one it was, but
You might have. I didn't even think about that.
yeah, I thought I crossed it off on one chapter's homework and then added it to the next one because it covered some stuff from both chapters. But
I went through every chapter while I was studying one day. I
yeah,
don't remember going over it, but
I will check that, and if I didn't, if it wasn't part of the homework, I will fix that in the exam. Okay. Anybody have a?
Chapter 10 that says it's in review mode because it's past the due date.
Yeah, all of them are past the due date now, I think. What is today?
Today is the 25th.
Yeah, which one did you have a question on? Excuse me.
I can't remember. It was one that I was getting wrong, but it's, I can't remember which one it is right now. Because it just shows, it doesn't show any of the scores.
Okay. Oh, you can't see your own scores?
I can, like, I know what I got overall if I go to grade, but I don't think it will show me the individual chapters.
Oh, that's kind of weird. What are you seeing on your screen right now, Cassidy? My whiteboard?
oh, I wasn't even looking at it. I was in homework.
Oh,
Yeah, I can see your whiteboard.
you can just see my whiteboard though?
Yeah.
Okay. I'm going to just take a look at a few things here really quick. Well, if nobody has any questions, we can finish up chapter 12. I don't have a problem with finishing up chapter 12 if nobody else does.
Is there any way that we could look at chapter 10 so I could ask those questions? Or
I mean, I could open it up again for you. That's easy enough to do.
that would be great. If we could.
Let's see. It's actually easier to go this way. Calendar. Chapter 10. Okay, you should be able to open it now. We're so close to being done.
Yeah, I still need to scan and send you my last lab. I was done with it like the day after you guys came, but I haven't scanned it yet.
That's okay.
And then whenever, like towards the end of this or whatever, I was going to ask if you could explain what you needed to for the lab.
Yeah, we'll do that for sure. So what I think I'm going to do here is I'm thinking I'm going to put together a chapter 12 homework really quick. And then let's see, what do we have? How much time do we have left in class? 2 weeks? 2.5 weeks? Almost 3 weeks now. We have this week and the next week and then the week after that. So 3 weeks. This week we'll finish up our fluids stuff. Let's see.
We meet 7 more times after today.
7 more, okay. Sounds about right. And then, so what we'll do, we'll finish up fluids this week. We'll do temperature next week. We'll try to hammer out most of temperature next week, and then do our waves and hearing the last week. It'll be kind of a big deal to hammer out temperature in a week, but we might take a little extra time. I'll give you chapter 12 homework today as well, so you can get started on both 11 and 12, and then we can. Let's see. We already did a lab this week, so we'll do a homework review tomorrow. We'll review homework for chapter 11 and 12 tomorrow, and then you guys can have till Monday to finish that up, and then Monday we'll start the temperature assignments.
So when will our final exam be then?
The final exam will be the last week of class, and it will be due that Friday, I guess. I guess the last day of class is technically Thursday, but we can have it due Friday, that last week of class.
On the syllabus it says the 11th is the last day or whatever.
Yeah. But it's not super set in stone or anything. So we can go to that Friday or even the next Monday if we need to.
And then also, will you have all of the labs graded and like all that stuff done like the week after, or how long will it take till everything's calculated?
When you finish your final, I should have your grade completed within a day or two after that.
Okay.
The labs are 20% of your grade, but for this particular class, the way that I grade them is I give you, for participation, I give you essentially 60% right off. If you were there, if you did the lab, you get 60%. Then the remaining parts of the lab are how I feel you understood it is about another 30%, and then how you did in your calculations and in your graphs and other things like that is another 30%. So most of it is just getting there and doing it, and most of my students are usually averaging about 90% on their labs or more, if they're putting any effort in at all. So they're taking any effort to do the work and to understand it, then they're getting 90+%. Usually it's a big advantage to your grade. Usually doesn't hurt anybody as long as they do the labs. So,
Okay.
and I'm terrible at grading labs during the semester. I know that. It's just one of my big weaknesses as a teacher.
No, it's okay. I have my chemistry teacher was like that.
Yeah, grading things is not my favorite. When I first started teaching for the first 4 or 5 years, I was really diligent at grading, graded every day and every night, and I was up till 2 in the morning, and I just burned myself out. And that's when I started using electronic grading more and more, the online grading systems, because I think it's important that students have feedback every day, but I just couldn't do it anymore. So I had to have a different way for giving them more feedback, and I think that these systems do a good job of that. Yes.
So I had a question.
Sorry, Leslie, just really quick. Leslie, you had a question that you asked very quietly. What did you?
I said I was going to be gone.
You were going to be gone next week. Okay. Well, it's a good week to be gone. These less difficult weeks are better weeks to be gone than the first few weeks. Of course, you were gone one of the first few weeks too. It makes it hard. But right now, I'm not really worried about anybody in the class. You guys are all doing pretty well and getting decent grades. So I'm very grateful to have good students right now. So just keep working hard. Okay, so what's your question? Sorry, go ahead.
Who's in the chapter 10 homework, number 5?
Chapter 10, number 5. Ah, yes.
So the downward and the acceleration of the block, it says that consider the block moving down to be positive. So it just wouldn't be gravitational, it wouldn't be 9 meters per second.
No. And the reason for that is, I can't remember how we did this when we did this in class, but I've done it probably 3 times since then with different students. And I think I've done it the same way every time since, but I just can't remember what we did in class. But so you may have notes that are different than this if you took notes in class.
Okay.
But anyway, this is what I think is the best way. You have this system where you have this pulley and this block winding string off of this pulley like this, right? This pulley has some radius r and some mass m, and this has some other mass big M, right? And they want to know something like what's the acceleration of the block, or what's the tension in the rope, or something like this, right?
Yeah, what's the acceleration, what's the downward acceleration, and then what's the angular, and then how long it takes to perform, how many radians to perform, and how many revolutions.
Okay, so one of the things that's important about this is to recognize the fact that you're going to have to accelerate this mass up here rotationally. There's an alpha for this pulley. And that means that there's going to have to be a torque to cause that alpha. Forces cause accelerations, torques cause angular accelerations. And torque is equal to the I times alpha, right? Where the I is dependent on the shape, this being a disk. You look that up and figure out what it is and plug in the formula for I for a disk. It's going to have a mass and a radius in it, and a radius squared in it rather. And then the alpha is the thing that they either want you to calculate or they give you or something else. But there is a torque involved. Because there's a torque involved, there is a force that is causing that torque. What is the force that causes this torque?
Gravity.
No.
Yeah.
The tension in the rope because of the weight of the block, right? The block is pulling on this rope and causing some tension that is creating a force at this wheel and causing the torque, right? So there's tension. There's tension pulling downward here. And where does it pull also? Where does the tension also pull? It pulls downward on the pulley, but where else does it pull?
Pulls upward on the block.
Pulls upward on the block, and so that counteracts gravity. The tension always acts on either end of the object that has the tension in, right? So this one pulls upward on the block and downward on the pulley. So this ends up being two problems. I'm going to split this problem right down the middle here. One problem is a tension that causes a block to accelerate. The other one is a tension that prevents a block from falling at its normal acceleration caused by its weight. So this one has a free body diagram with tension up and weight down. This one has a free body diagram with tension and that's causing a torque, right? So what is the equation that what are the equations we're going to use? Well, up here the tension is going to equal, the torque is going to equal the tension, the force, times the distance to where the force is acting, the R, T times R, right? Times the sine of the angle, which is 90, so that's just 1. So this is the equation for the first one. Tension times R equals I times alpha.
Okay.
The second one has an equation that's going to be the sum of the forces in the y direction equals what?
0.
Is it accelerating?
Not yet until it starts moving. Right?
Yes, but in the problem, does it talk about accelerating? Yes, it does. So it's not equal to 0, it's equal to mass times acceleration.
Mm-hmm.
The big mass, right? Times acceleration. So this one, and then what are the forces involved? We have plus tension minus weight, right? So this is the equation here for this problem. But these equations are related to each other in a couple of different ways. Both of them have the tension in them, right? But also the alpha and the A are related because the string is connected to this pulley. So alpha equals, well, R times alpha equals, that is terrible. R times alpha equals A, right? So you can replace the alpha with A over R or the A with R times alpha, right? And then you can solve one of these equations for T and plug it into the other one and solve for either A or alpha. Once you've got A or alpha, you can solve for the other one. And once you've got those, you can solve for T.
So you say I don't want to plug it in where there's no division. So I plug in R times alpha for the A and the mass times acceleration.
Yeah, plug that in right here, and then you have two equations with two unknowns. You have alpha and T. Plug one, you solve one of them for T, plug it into the other,
Okay.
right? Or solve one of them for alpha and plug it into the other. Either way. And then you're good to go. Any other questions?
I got one more. I'm just writing this down.
Bought some pot stickers at the store today, Packer. They were decent. There might be some left over, but there might not. There were some when I left home. But if there aren't, we'll go get some.
So just making sure I got it right. So I solved one of the equations, the one on the bottom.
Yep.
With pen by.
Solved it for T,
Yeah, tension equals.
MA plus W.
Huh?
MA plus W, right? Or MR alpha plus W.
Yeah, MR alpha plus W. And then my other equation currently says T times R equals, I substituted the moment of inertia into the one that equals MR squared over 2 times alpha.
Okay.
So then I substitute what I solved in the other equation in for T and then solve for alpha, right?
Yeah, sure.
Okay.
That'll work.
Okay. And I also had a question questions about number 6. So I was able to get the initial angular acceleration, or the angular velocity rather, but as soon as it starts to roll up the hill, even further.
Okay, so this one is very much a conservation momentum problem. So we start off like this, and then we're going up a hill, right?
Uh-huh.
At the beginning, we have what kinds of energy? Let's call this y equals 0. This is height equals 0. Good night.
So at the beginning, you just have rotational and
So we have
linear kinetic energy.
rotational, which is 1/2 what?
1/2 I omega squared.
That's rotational kinetic energy.
And then you have the 1/2
Translational kinetic energy, 1/2 mv squared, right? And the I for a ball is like 1/12 something or 1/6 something, whatever it is.
And then that
Right.
will just equal, you have the same pieces over there plus the.
So you also have 1/2 I omega squared on this side as it's rolling still, right? But this is now final plus, and it's also moving linearly, so there's still some velocity to it, mv final squared. But we also have what?
Gravitational potential energy.
We also have m times g times h, where the h is this new height, right? Now, again, because it is rolling along this edge and it's not slipping, the v's and the omegas are related. So you can eliminate one variable here.
Okay.
You can
omega
you can
equals VR, right?
no, it's the other way around. It's always
V equals omega R.
v equals omega. Remember that omega is measured in angle, which has no units, right? Well, omega does have units, but angle doesn't have units, so it's just per second. So you need to make it meters by multiplying by r, right? So it's meters per second. So if you multiply your omega by r, you get v, and so you can replace each of your v's with omegas times r's, but they're v squareds. So be careful. V squared does not equal r times omega squared.
It equals R squared.
R squared times omega squared.
And I
Right.
already figured out, if it gave me the velocity, like the V,
Mhm.
I was able to figure out the omega correctly, so
Yeah.
then I can, what would the step be to get to the linear and angular acceleration?
Oh, so to get to linear and angular acceleration, when do they want you to calculate that?
As
As
the
it-
hollow sphere rolls up the hill.
so as it's rolling up the hill, what is its angular acceleration and linear acceleration? Is that what it's asking for? Okay. So
Just one question real quick. It says it's a hollow sphere, so would I use for the Roman inertia, would I use the one that it describes it as thin spherical shell without any diameter?
that's correct.
Okay.
So remember that angular or that acceleration has a couple of different ways you can calculate it. And one of the simplest ways is just this. V final minus V initial over time. Right? And the same thing for angular. Omega final minus omega initial over time. So once you use this equation to find your final velocity, you can also find your final angular velocity, and then you can just find your accelerations from this.
Okay, but you're using, so for the acceleration, for that to work, I'd have to figure out how long it took it to stop rolling, right?
Oh, it didn't tell you a time.
No, it didn't.
No, but you have a distance. You can do a distance, right? Well, do you have a distance? Let's see.
It gives us the mass and radius of the hollow sphere, its initial velocity, and then the incline that it
Gives you the angle of the incline. Let's see. Might have to use kinematics for that.
That's what I was afraid.
Let me go
That's
take a
what I
look.
found. It works so well.
If you're going to use kinematics for that, it's in 2 dimensions for the acceleration, but for the linear acceleration. But for the angular one, let's see here. For the angular one, we might be able to do it. Acceleration. You actually can probably use geometry to do it because well, this is another thing that we talked about this. We used this once or twice, but let's look at it really quick. So as you're going up the hill, you have this different kind of thing that's going on. So here's our hill. Here's our angle theta right here, right? And there is a force that is on this side. Sorry. Your weight force from the ball is not sitting over the top of the point of contact with the ground like that. See that? That creates a situation where you have a torque. And this is what's going on. This is the weight right here. And you have the angle theta right here. Right? And you have the R here. This is your R distance right here. So you have a torque that is causing your angular acceleration, your angular deceleration, which is equal to the weight of the ball times the vector r, the radius of the circle, but it's now times the sine of the angle theta, which is the incline of the ball. That torque is causing your angular acceleration. It's equal to I times alpha. But it's also causing linear acceleration when you multiply alpha times r.
Okay, so that's how we're going to approach it.
So this one can give you alpha, and then you can get acceleration, A.
Okay, and then once I know the linear and angular acceleration,
You can calculate the time.
How long it takes. And,
You can use angular kinematics to do that. I would use angular kinematics to figure out the time as well from the alpha. You can do that.
Okay, thank you.
Yeah, that's definitely the hardest problem I think I gave for chapter 10.
I would
That's
appreciate
okay.
kick my butt.
It's a tough one. Any other questions at all? All right, let's take a look at some chapter 12 homework assignments really quick. Homework problems, and put those together for you. What time is it? Do we have time yet? Or we got time?
16.
We got time. We're good. All right.
I just want to, on those questions for chapter 9 that we went through together,
Yep.
number 9 with the cat,
Yeah.
did not get an answer. That
The
was,
cat on the merry-go-round?
No, the cat on the pier. I just gave up and
Oh.
took my grade because it would be dropped anyways.
The
But
cat on the pier?
I gave up because we did it the one time in class and we had an equation made for it, and we had, when you and I had a session and had that one, and I could not get anything close.
Okay, you want to do it really quick?
I mean, for your final exam, you take questions from your previous exams, right?
That is correct.
Okay, then I'm not worried about it. I gave up.
So I did this. Let me just recap a little bit, really quick with this problem. I did this two different ways. The first time I did it, I decided to split the board in two and treat it like two separate boards, with two separate weights on it that created torques, which is perfectly legal. It's just a little more work. The second time I did it, I decided not to do that because I realized it wasn't necessary, and I treated it as a single board with a weight in the middle and a weight from the sardine can out here, and then the weight of the cat somewhere in between at some distance x from one end of the board or the other, or from the end of the pier or whatever. The hardest part of that problem was sorting out all the distances, because you want to measure the distances to every force from the same point, but the board is sticking out over the edge and you want to know the distance from the edge. So that was the hard part. So those are, and then you end up doing, some of the forces in the y direction, and then some of the torques about a single point, and you solve them both. But just as a recap for how I did that, how I approached that problem two different ways. And if you don't need to see it again, then we're fine and we'll move on. That's good.
I just took the zero, the big old egg, and just accepted it.
Okay. Well, let's take a look at some Chapter 12 problems really quick. I have to add a Chapter 12 assignment here.
I just finished the chapter 11 questions,
Oh, wow.
and there was one of them that I was clicking too fast because I was being dumb. And I know what this other check box is. I don't know if you'll give me points for it, but
Well, send me an email.
it won't let. There's no ask your instructor about this question.
Oh, really? Oh, you can just send me an email within the system, or just a regular email or whatever. That'll work too. Let's see.
Not really a big deal. You don't.
All right, so let's make this let's make it do Monday or July 31st. Sounds good. All right. Fluid dynamics we're doing now. Bernoulli, flow rate, turbulence, Poisson. Oh, you gotta be kidding me. There's only 3 questions? Obviously, that's not going to work. There's only 2 questions. Somebody has not added any questions here. I'm going to have to go make my own. You gotta be kidding me. Obviously, people think that this is as important as I think it is. It is important stuff, but there are other things that are, I think, more important. Let's look one more place here.
Mr. Daly.
Yep.
The Archimedes principle, what's like our fully expanded formula, like, I know the buoyant force equals the weight of the fluid. And the weight of the fluid is equal, it's the volume, density, and
Volume times density.
just volume times density.
Oh, weight of the fluid?
Yeah,
Weight of the fluid is volume times density times
times gravity.
G. It looks like there are no questions for this. So we have two choices. We can either make some questions or just skip them. I think I'll make some questions, but it'll take me some time. So I'll have to put aside entering some questions into this homework assignment, and I'll try to get those done. I'll try to get some done tonight, but we'll definitely have to wait on that. Excuse me. All right. Well, as far as anything else goes, I don't have anything else that I need to share with you guys. So, you guys want to break a little early today? We can.
I'm almost home. So good.
So, homework was really that easy, huh? What's that? Yeah, we do. We definitely need to talk about the other class. So,
Yep.
and I need to talk to Cassidy really quick about the lab. So, all right. So, Cassidy, let's talk about the lab. There are, I think, 3 different experiments. Is that right? Part 4 different experiments. So, what you're going to be doing is you're going to be putting different objects into a fluid. And I don't know if I provided you with enough stuff to put into a fluid. You'll need a couple of different metals that you can measure the volume of easily, like a cube or a cylinder. A cylinder is best, but did I send you some? I sent you some brass weights, didn't I?
Yeah.
Are any of them cylinders?
Yeah.
Okay.
Like the cylinder with the little knob on top to tie things onto.
Okay, so you can use that. That'll work decently. It's not ideal because of that little knob on top will add some volume to it. But you could also, if you wanted to, you could use like some bolts from the garage or something if your dad has any bolts in the garage. And ideally, you need something that is made of 2 different materials, because you'll need 2 different materials that you can submerge. And you can just put them onto a string and tape them onto a string so that you can put them under the water. But you just need to be able to measure their volume somehow. It's ideal if you can have something like a cube or a rectangle or a cylinder that's easy to measure, easy to calculate the volume of. Let's see here. So what you want to do, I'm going to put up my whiteboard again here really quick. So I know that you have limited tools there that I've sent you, but hopefully you can figure out a way to do this with these tools and other things that you might have at home. But the idea is to have a container of liquid, maybe on the floor, and then above it to have your force measuring device that I sent you hanging above it on a rod like this, so that you have a rod going through the little hole that has the screw in it. There's a screw up here that tightens it onto a rod. I think I've given you a rod. And so you could like tape this down or weigh it down on top of a table or something above your water. And then on the hook down here, you'll hang the different objects. And sometimes you'll hang them in air to measure their weight. And then sometimes you'll hang them in the fluid. You'll lower them in the fluid or raise the fluid into them so that you can measure their weight in the fluid and out of the fluid. Does that make sense?
Yeah.
Okay.
So I'm measuring the weight in and out of the fluid. fluid.
That's correct. And that's what you're doing in part 1, the first experiment.
So I know that I have the force sensor, and I have the rod with like the screw, like glue
Yep.
plug,
Yep,
or whatever.
yep.
And then you said that there's a bolt I'm supposed to have.
Well, you can use a bolt. What you need you need 3 different objects that you can put in the water. So the objects work best if they're rectangular or square, because that's very easy to measure the volume of, because the volume is equal to the length times the width times the height, right? Or if they're cylindrical, like a bolt that you might get out of your garage or something. If you have a bolt or a cylinder of metal or something, then the volume is just equal to pi times the radius of the bolt squared, right? Times the length of the bolt. So there's your volume for a bolt, and that's why it's just easier to have either rectangles or bolts. And if you can find objects like that, that'll be great. We need 2 different metals or 2 different things that will sink. Is better to say it that way. So you could even use like an old battery would be ideal. An old AAA or AA battery would be great, or even a bigger one if you're using a bigger thing for your fluid. That would be a good one. I don't know if those sink or float, but you'll need 2 things that will sink in the water and 1 thing that will float in the water. And a wood dowel or just a rectangular piece of wood would be good for a wooden one. So. But anyway, in the first one, you're just submerging things that will sink under the water and weighing them out of the water and weighing them in the water, and then you're doing some calculations with that. In the second one, although in the second one you're doing a little bit different. In the second one, you're going to measure where the water is. Now, did I send you a graduated cylinder? Do you know what a graduated cylinder is?
Yeah, no. Good.
Do you have access to one?
Maybe I could call my old science teacher up.
Yeah, if you could get one, that would be ideal for this. So, yeah, a graduated cylinder would be ideal, because then because in the second one, what you're going to do is you're going to lower this in here, and you're going to measure how high the water goes up, and you're going to measure the change in volume, and then you're going to calculate the weight. You're going to calculate the weight of the water that you displaced. That's what's happening in the second one. In the third one, you're measuring the volumes of the volumes of the things that you're going to put in there. And then in the fourth one, you're doing the floating, you're doing like the wood for the floating one. So, but all of them have pretty good instructions and things that the equations are in there and everything.
Yeah, this is really funny. I actually did this same lab, well, maybe not like this one,
But a very similar one?
Yeah, because my science teacher, she had those blocks of the different materials.
Yeah.
So I messaged her and was going to ask if she would be here. She doesn't live here, so I don't know. But
Well,
if
if you can figure out how to get a graduated cylinder, you should be able to do this fairly well with stuff around your house. If you can't get a graduated cylinder, the other option that you have is to measure the cross-sectional area of the container of water that you're using, and then measure the height that it goes and calculate the volume that way. So the cross-sectional area times the height would give you that volume, that change in volume, times the change in height. That's the other thing you could do. And then you could just mark on there where it goes to. Does that make sense?
Yeah, it does.
So just make do with what you can, and if you can get the parts to do it, great. If you can't, just kind of try to do what you can and turn it in.
Okay.
Any other questions?
I don't think so.
All right. Well, you have a good one. We'll see you tomorrow.
Okay. See you later.
Bye.
Bye.